Welcome to today's paper reading. Today's paper is titled, Clearer Frames Anytime, Resolving Velocity Ambiguity in Video Frame Interpolation. This paper was published on AR14 by Zhihang Zhong and colleagues from Shanghai Artificial Intelligence Laboratory and SNAP Inc. Existing methods for video frame interpolation, known as time indexing, struggle with predicting precise object movements due to the infinite possible trajectories an object can take between two frames. This often leads to blurry frames as the method averages out these possibilities. In contrast, our novel approach, distance indexing, provides the network with an explicit hint on how far the object has traveled, reducing the uncertainty tied to object speeds and offering a clearer learning goal. Even with this guidance, long-range motion can still result in blurry objects due to directional ambiguity. To address this, we propose an iterative reference-based estimation strategy that breaks down long-range predictions into several short-range steps, resulting in markedly sharper outputs and superior perceptual quality. Video frame interpolation (VFI) is essential for applications such as creating slow-motion videos, video generation, prediction, and compression. However, directly warping frames using optical flow often results in linear motion modeling, which can diverge from actual motion paths and lead to artifacts like holes. The primary challenge in learning-based VFI is velocity ambiguity, where models receive identical inputs with differing supervision signals during training, leading to blurred and imprecise interpolations. To address this, the authors propose distance indexing and iterative reference-based estimation, which enhance the capabilities of arbitrary time interpolation models and improve interpolation quality. Figure 1 illustrates the differences between time indexing and distance indexing training paradigms in video frame interpolation (VFI). In time indexing, the model uses the starting frame I0, the ending frame I1, and a scalar variable t as inputs. This method struggles with predicting precise object movements due to velocity ambiguity. In contrast, distance indexing replaces the scalar with a distance map dt, which specifies how far objects have traveled between the start and end frames. This approach offers a clearer learning goal for models, reducing uncertainty tied to object speeds. Additionally, distance indexing can incorporate iterative reference-based estimation to further address velocity ambiguity, resulting in notably sharper predictions. This plug-and-play strategy can be integrated into existing VFI models without architectural modifications, enhancing their performance in arbitrary time interpolations. In the realm of video frame interpolation, VFI, numerous methods rely on optical flow to predict latent frames. These methods typically warp input frames using flow calculated by networks like those referenced in 6, 12, 37, 38, or self-contained flow estimators such as 11, 21, 50. Networks then refine the warped frame to enhance visual quality. Advanced flow estimation techniques include depth-aware flow projection layers, estimating kernel weights and offset vectors for each target pixel, and addressing large motion interpolation through recursive multiscale structures. Additionally, the use of transformers and efficient pyramid network designs has been employed to model long-range pixel correlations and achieve high-quality, real-time interpolation. Figure 2 illustrates the concept of velocity ambiguity in video frame interpolation (VFI). Part A demonstrates speed ambiguity, where the exact location of an object at a specific time step is uncertain due to unknown speed distribution. Part B shows directional ambiguity, where the direction of motion is indeterminate, adding complexity to model training and inference. These ambiguities, collectively referred to as velocity ambiguity, are particularly pronounced in arbitrary time interpolation, complicating the prediction of a continuum of time steps. Figure 3 illustrates two strategies designed to address velocity ambiguity in video frame interpolation (VFI). Part A shows distance indexing, where a distance ratio map, dt, is directly specified instead of relying on an uncertain time-to-location mapping. This method helps the model interpolate more precisely by sidestepping the intricate process of deducing the time-to-location mapping. Part B depicts iterative reference-based estimation, which divides the complex interpolation for long distances into shorter, easier steps. This strategy enhances the traditional VFI function by incorporating a reference image and its corresponding distance map, thereby reducing uncertainty in each step. Both strategies are designed to be plug-and-play, seamlessly integrating into existing VFI models without necessitating architectural modifications. The concept of velocity ambiguity in video frame interpolation, VFI, encompasses both speed and directional ambiguities. Speed ambiguity arises because the exact speed of an object, such as a baseball, is unknown. This uncertainty can lead to multiple possible positions for the object at a given time, complicating model training. Directional ambiguity further complicates matters by introducing uncertainty about the direction of motion. For arbitrary time interpolation, where the network must predict a range of time steps, the ambiguity becomes even more pronounced, leading to what is sometimes referred to as mode averaging. These ambiguities collectively result in challenges that need to be addressed to improve VFI models. The authors introduced two strategies to address velocity ambiguity in video frame interpolation. The first strategy is distance indexing, which uses an off-the-shelf optical flow estimator, RAFT, to determine a pixel-wise distance map. This map is calculated by projecting the motion vector from I0 to it onto the vector from I0 to I1. By integrating this distance map, the network can achieve sharper frames during inference. The second strategy is iterative reference-based estimation, which divides long-distance interpolation into shorter steps, using a reference image and its distance map to reduce uncertainty. During inference, a uniform distance map is often sufficient, approximating constant object speeds and achieving higher perceptual scores in user studies. Figure 4 illustrates the process of calculating the distance map for distance indexing. The figure shows the use of RAFT, an off-the-shelf optical flow estimator, to determine the pixel-wise distance map. Given an image triplet, I0, I1, the optical flow from I0 to it, denoted as V0t, and from I0 to I1, denoted as V01, are first calculated. At each pixel x, y, the motion vector V0t, x, y, is projected onto V01, x, y. The distance map is then defined as the ratio between the projected V0t, x, y, and V01, x, y, which helps the network achieve a clear comprehension of distance during its training phase, leading to sharper frames during inference. In this experiment, the authors integrated their proposed distance indexing and iterative reference-based estimation strategies into various video frame interpolation (VFI) models. These strategies were seamlessly incorporated into influential models like RIFE and IFRNet, as well as state-of-the-art models such as AMT and EMA-VFI. The integration was conducted using the Vimeo 90K septuplet dataset, which includes 91,701 7-frame sequences at a resolution of 448 by 256. The evaluation of these models was based on both pixel-centric metrics like PSNR and SSIM, and perceptual metrics such as LPIPS and NIC. Additionally, the convergence curves of different model variants were analyzed to substantiate the efficacy of the proposed strategies. Figure 5 presents a qualitative comparison of various versions of arbitrary time video frame interpolation (VFI) models. The base model, labeled as T, uses time indexing. Enhanced versions include models using distance indexing (D), iterative reference-based estimation with time indexing (TR), and a combination of both strategies (DR). All models utilize uniform maps for reference. The figure allows for a detailed visual assessment of the improvements brought by each enhancement strategy. Figure 6 presents the convergence curves for different model variants, denoted as TD and DR. The traditional time indexing model, T, produces blurry results with indistinct details. In contrast, the distance indexing model, D, significantly improves perceptual quality, offering clearer interpolations. The combined approach, DR, provides the highest quality across all base models, highlighting the synergistic effect of distance indexing and iterative reference-based estimation. This figure underscores the effectiveness of these techniques in enhancing the performance of advanced arbitrary time video frame interpolation models. Figure 7 presents the results of a user study evaluating the performance of 4 model variants, TD, TR, and DR. The horizontal axis represents user rankings, with number 1 being the best and number 4 the worst. The vertical axis indicates the percentage of times each model variant received a specific ranking. Each model variant was ranked an equal number of times. The model D.R. emerged as the top performer, reinforcing the effectiveness of the distance indexing and iterative reference-based estimation strategies. All models in the study used uniform maps. Figure 8 illustrates the process of manipulated interpolation of anything, a novel capability enabled by distance indexing in video frame interpolation (VFI) models. The workflow begins with the use of segment anything (SAM) to generate object masks for the starting frame. Users can then customize the distance curve for each object delineated by the mask, effectively controlling its interpolation pattern. This customization allows for unique distance map sequences to be generated, leading to diverse interpolation outcomes. One of the primary applications of this technique is retiming specific objects, as demonstrated in the supplementary video. Table 1 presents a detailed comparison of various model variants on the Vimeo 90K septuplet dataset. The table highlights the performance of models using different indexing paradigms and estimation strategies. Notably, the combined model, D.R., which employs both distance indexing and iterative reference-based estimation, demonstrates superior performance in perceptual metrics like LPIPS and NIC. This table serves as a comprehensive guide to understanding the impact of different strategies on model performance, particularly in the context of video frame interpolation tasks. Table 2 presents an ablation study focusing on the impact of varying the number of iterations on the Vimeo 90K septuplet dataset. The study uses different methods such as RIFE, IFRNet, AMTS, and EMAVFI, each tested with 1, 2, and 3 iterations denoted as 1, 2, and 3 respectively. The performance is evaluated using metrics like LPIPS and NIC, which measure perceptual similarity and naturalness of the interpolated frames. The results indicate that the number of iterations significantly affects the quality of the interpolated frames, with optimal performance often achieved at specific iteration counts for each method. Table 3 presents a comparison of the performance of x8 interpolation on the Adobe 240 dataset using the RIFE 11 method. The table likely includes various performance metrics such as LPIPS and NIC, which are crucial for evaluating the quality of the interpolated frames. However, the specific metrics and their values are not provided in the given context, making it difficult to summarize the exact performance differences. This table is essential for understanding how the RIFE method performs under high interpolation factors on a well-known dataset like Adobe 240. Table 4 presents a comparison of x8 interpolation performance on the X4K 1000 fps dataset using the RIFE method. The metrics evaluated include PSNR, SIM, LPIPS, and NIC. The PSNR values range from 36.26 to 36.80, indicating the quality of the interpolated frames. SSIM values, ranging from 0.964 to 0.967, show the structural similarity between the original and interpolated frames. PIPS values, ranging from 0.032 to 0.040, measure the perceptual similarity, with lower values indicating better performance. Additionally, NIC values, ranging from 6.924 to 7.130, assess the naturalness of the interpolated images. Table 5 presents a detailed comparison of the performance metrics for x16 interpolation on the X4K 1000 fps dataset using the RIFE method. The table likely includes metrics such as PSNR, SSIM, LPIPS, and NIC, which are crucial for evaluating the quality and accuracy of the interpolation process. This comparison is essential for understanding the effectiveness of the RIFE method in handling high-resolution video interpolation tasks, particularly at 8x16 scale. Researchers and practitioners can use this data to benchmark their own methods against RIFE and to identify areas for potential improvement in video interpolation techniques. Table 6 presents a comparison of interpolation results on the Vimeo 90K dataset using the Jian flow method for distance map calculation in conjunction with the RIFE model. The table highlights performance metrics such as PSNR, SSIM, LPIPS, and NIC, which are crucial for evaluating the quality of interpolated frames. These metrics provide a comprehensive view of how well the Rife model, when paired with GM flow, performs in generating plausible frames with high perceptual quality, addressing the challenges posed by velocity ambiguity in video frame interpolation. In this study, the authors challenged the traditional time indexing paradigm, addressing its uncertainties related to velocity distribution. They introduced distance indexing and iterative reference-based estimation strategies, offering a transformative approach to video frame interpolation (VFI). These innovative plug-and-play strategies not only improve performance in video interpolation but also provide users with granular control over interpolation patterns across various objects. Future research will focus on estimating accurate distance ratio maps from multiple frames, which has potential applications in a range of tasks that employ time indexing, such as space-time super-resolution, future predictions, and blur interpolation. Thank you for watching.